Good morning once again, everyone. Welcome to Introduction to Logic, Deductive and Inductive Reasoning. We are now at our week 10, and our topic is about Venn diagram. And for this week, we will define what is a Venn diagram and its uses, also represent sets using a Venn diagram, and differentiate the kinds of set. So let's proceed to our discussion. For this PowerPoint presentation, I will show you a video discussion regarding about Venn diagram.
Another method of symbolizing categorical propositions is the use of the Venn diagram. John Venn, who introduced the method, thus the name Venn diagram, used two overlapping circles to represent the relationship between two classes. Consider these diagrams. The shaded portion represents a class that has no members, while the area with an X signifies that the class has at least one member. Generally, this is what a Venn diagram looks like. Where this is read as S but not P, and this represents the class of things that are part of S but are not part of P. And this is read as not S but P, and this represents the class of things that are part of P but are not part of S. And this is read as S but P, and this represents the class of things that are both parts of S and P. Now, let's discuss the Venn diagrams that are used to represent the four standard types of categorical propositions. Here is the Venn diagram for universal affirmative A propositions.
My job is to make college easier because students have a lot on their
Sorry, Coach. Skip that participants, very important participants.
The shaded area of this Venn diagram represents a class that has no members. Thus, in the Venn diagram for a universal affirmative A proposition, the area S but not P is shaded to indicate that all members of S are members of P. Thus, we say all S are P. Next is the Venn diagram for universal negative E propositions. The shaded area of this Venn diagram represents a class that has no members. Thus, in the Venn diagram for a universal negative E proposition, the area S but P is shaded to indicate that this class has no members. Thus, we say no S are P. Then we have a Venn diagram for particular affirmative I propositions. A particular affirmative I proposition asserts that there is at least one member of S that is a member of P. This is diagrammed by placing an X in the area S but P, which is common to the two classes. Thus, in the diagram, we place an X in the area S but P, and we say some S are P. Now, here is the Venn diagram for particular negative O propositions. And so, a particular negative O proposition asserts that there is at least one member of S that is not a member of P. Thus, in this diagram, we place the X on the area S but not P to indicate that indeed there is at least one member of S that is not a member of P. Thus, we can say some S are not P. Now, in traditional or Aristotelian logic, one assumes that universal affirmative A and universal negative E propositions have existential import. Thus, in the example, all angels are holy, one assumes that there are angels and that all of them are holy. However, in applying the Venn diagram, one does not make this assumption. In the Venn diagram, all angels are said to be holy only if there are indeed angels. But the Venn diagram for a universal affirmative A proposition does not contain an area in which there is a symbol to show that there is an angel. Hence, the propositions all angels are holy or no angels are holy are non-existential propositions. In the first place, there are no angels in reality. This Venn diagram demonstrates this point. As we can see, both application of traditional rules and use of the Venn diagram presuppose that only particular affirmative I and particular negative O propositions have existential import. Thus, a Venn diagram for the particular affirmative I proposition, some angels are holy, contains an X to show that there is at least one angel that is holy. And this is how the Venn diagram looks like. A Venn diagram can be used to show the validity of categorical syllogisms. 3 intersecting circles are needed to diagram a categorical syllogism. 1 circle for each class. The following rules will be observed in testing the validity of syllogism using a Venn diagram. Rule number 1. The universal premise should be diagrammed first if the argument also contains a particular premise. Rule number 2. The letter X should be placed on the line dissecting an area if the whole area is so designated in the premise. Rule number 3. Only the premises should be diagrammed. And rule number 4. If the conclusion is self-evident in the diagram, then the argument or syllogism is valid. Let us consider this example, which is already in its standard form. All M are P. All S are M. So all S are P. Now, how do we determine the validity of this syllogism using a Venn diagram? Well, first, we need to draw 3 intersecting circles, that is, circles for S, P, and M, and then number the areas by starting at the center and then clockwise. Now that we have drawn 3 intersecting circles, each for S, P, and M, our next task is to diagram the syllogism. Let us start with the first premise, that is, all M are P. It must be noted that since the premise talks about the circles for M and P only, so we will imagine that the circle S does not exist. Hence, we will diagram M and P only. Now, since the premise says all M are P, that is, all members of M are members of P, then we will shade areas 5 and 6 to show that all members of M, which are areas 1 and 4, are part of P. The Venn diagram of the syllogism now looks like this. After we diagram the first premise, let us proceed to diagram the second premise, which reads, all S are M. This time, the premise talks about S and M only, so we will imagine that the circle for P does not exist. Now, since the premise says all S are M, that is, all members of S are members of M, then we will shade areas 7 and 2 to show that indeed all members of S, which is area 1, are part of M. Now the diagram looks like this. Since the Venn diagram of the syllogism is now complete, let us proceed to analyze the diagram to determine whether the syllogism is valid or invalid. As rule number 3 says, we diagram only the premises. Hence, we do not diagram the conclusion. And as rule number 4 says, the argument or syllogism is valid if the conclusion is self-evident in the Venn diagram. Now the conclusion says, all S are P. As we can see in the Venn diagram of the syllogism, this conclusion, all S are P, is perfectly diagrammed. That is, it is self-evident. In fact, since areas 2, 6, and 7 are shaded, then they do not exist anymore. What is left now of the class S is area 1, which all belongs to P. Thus, this syllogism is valid. Let us consider another example. Some M are P. All M are S. So, some S are P. And so, let us draw 3 intersecting circles for this syllogism, each for S, M, and P, and then number the areas by starting at the center and then clockwise. As rule number 1 says, we will diagram first the universal premise if the syllogism also contains a particular premise. Since the first premise in the syllogism is particular, while the second premise is universal, then we will diagram first the second premise, that is, all M are S. The second premise says, all M are S. So we will shade areas 4 and 5 to show that all members of M, which are areas 1 and 6, are part of S. And so the Venn diagram of the syllogism will now look like this. Now let us proceed to diagram the second premise, which says, some M are P.
Horrific.
Since this is a particular proposition, then we will not use the shading method. Instead, we will place an X on the designated area. Since the premise says some M are P, and since area 4 is already shaded, then it does not exist anymore. Thus, we will place the X on the area 1 to show that indeed there is at least one member of M that is a member of P. The Venn diagram of the syllogism now looks like this. Now that the Venn diagram of the syllogism is complete, let us proceed to determine its validity. And so, again, rule number 3 says, we diagram only the premises. Hence, we do not diagram the conclusion. And as rule number 4 says, the argument or the syllogism is valid if the conclusion is self-evident in the Venn diagram. Now, the conclusion of the syllogism says, some S are P. And if we look at the Venn diagram, there is an X on area 1, which indicates that there is at least one member of S that is a member of P. Hence, the conclusion which reads, some S are P, is perfectly diagrammed in the Venn diagram. Indeed, the conclusion is self-evident, therefore, the syllogism is valid. Here's another example. Some M are P. All S are M. So some S are P. Let us draw 3 intersecting circles for this syllogism, each for S, M, and P, and then number the areas by starting at the center and then clockwise. As we already know, we will diagram the universal premise first, which is all S are M. Thus, the Venn diagram of the syllogism now looks like this. Then let us diagram the second premise, which says, some M are P. Since areas 1 and 4 are so designated in the premise, then we will place the X on the line that dissects areas 1 and 4 to show that the whole area is so designated. Hence, the Venn diagram of this syllogism now looks like this. Since the X is on the line that dissects areas 1 and 4, this gives us an inconclusive reading of the conclusion. For this reason, this syllogism is invalid. Indeed, the conclusion is not self-evident. It is not perfectly diagrammed. Let us analyze one more example. All M are P. No S are M. So, no S are P. Again, let us draw 3 intersecting circles for this syllogism, each for S, M, and P, and then number the areas by starting at the center and then clockwise. Now, let us first diagram the first premise, which reads, all M are P. The Venn diagram of the syllogism now looks like this. Then let us diagram the second premise, which reads, no S are M. The Venn diagram of this syllogism now looks like this. The conclusion of this syllogism, which reads, no S are P, asserts that no members of S should be a member of P. But area 2 of the Venn diagram, which is also an area of S but P, is not shaded. Thus, the Venn diagram does not perfectly diagram the conclusion. Indeed, the conclusion is not self-evident. Therefore, the syllogism is invalid. That's it for now. Thanks for visiting us today for another whiteboard discussion here at Philo Notes. Full transcript of this video is available at philonotes.com. And to keep you updated of our newest videos, simply click here and subscribe and tap the bell for notifications. Thanks! Take care!
Hi.
So we will watch another video about the different kinds of set for Venn diagram. So we have here a video of Miss Linday Duhaday. So let's watch her discussion about the subsets or the different kinds of sets for Venn diagram.
Diagram is a way to describe sets with pictures. And often when we're doing math, that if we can have a picture of it, we can make more sense of it. And this absolutely happens with Venn diagrams. It's really easy to draw a picture and see what it is you're talking about. A Venn diagram has this concept of a universal set. And this is what the U is, and it's the entire rectangle. So the sets are inside the universe. So we see set A and set B, and they're inside the universe. And we're really talking about what is that universe? Well, it's all the elements in a particular context. And it can vary. And sometimes it's specified, and sometimes it's just apparent and doesn't have to be specifically specified. So in this case, let's look at this. We have a set A, and it has elements 1, 18, 31, 22, 42, and 7. So all those elements are in A. We have another set B that contains 31, 12, 42, and 16. And we see that there's two numbers, 31 and 42, they're in both sets. We see that A has 4 elements that are not in B, and B has 2 elements that are not in A. But all of them are in the universal set. And that's that rectangle, the universal set. Well, what is the universal set in this case? Well, when we look at this, it could be the natural numbers, right? Because all of these are natural numbers. It could also be all integers, which is, the set Z. So it could be set Z because they're all integers. It could also be Z plus because they're all positive integers. All of those work for the universal set. Even a universal set of 1 to 100 works for this case. And notice that in this case, it doesn't really matter which one of these are the universal set. We get a feel for what values are allowed in this particular universe by just knowing what elements are in A and B. Here's another example of varied universal set. So here's a set of people, right? And so the universe could be all humans, right? And that could be the universe in this case. Or another universe might be soccer players, because all of these are soccer players. Or the universe might be professional soccer players, so soccer players who get paid to play soccer. So the universe could be any of those in this case. And often it's not described what the universe is, but you can tell by context what it is, or a variety of ones that it could be. Another thing that we can identify is a subset. So if we look at this particular Venn diagram, we see 3 sets. So there's A, and there's B, and there's C, and we see some overlap. So that means that there are elements that are common between A, B, and C, and elements that are common between A and C, and elements that are common between B and C. But notice how B is entirely inside C. That means every element in B is also an element of C. And that makes B a subset of C. And that's by definition what a subset is. Every element in the subset is also an element in the superset. So that's a subset. And the way we do that, notice we get a new special character, and that is a subset. And notice that A is not a subset of C because A has some elements that are not in C. And C is not a subset of B because C has some elements that are not in B. And B is not a subset of A because B has some elements that are not in C. So in this particular Venn diagram, the only subset is B, and B is a subset of C. Now, the empty set is a subset of every set. So it's a subset of A, it's a subset of B, and it's a subset of C. So the empty set is a subset of every set. Now notice what happens when we have B and C, two different sets that are equal. So here is a Venn diagram that shows that B and C are equal, which means B is a subset of C because every element of B is in C. And also C is a subset of B because every element in C is also in B. This is also a subset. Then there is this thing called a proper subset. And this is the one that excludes them being equal. So a proper subset, they're not equal. And that's what it means by proper, is that they're not equal. And notice there's another designation here for it. This is the subset without the and equal, right? So this says it's a subset, but they're not equal. So B is a subset of C. And this means, in fact, B is a proper subset of C. B is also a regular subset of C. But C in this case is not a subset of B. It's not a proper subset of B, and it's not a regular subset of B. The empty set is a proper subset. It's a proper subset of B. It's a proper subset of C. So it's not only just a subset, it's a proper subset.
So
A Venn diagram is a way.
those are our video discussion for week 10. So we have defined what is a Venn diagram and its uses, and we had also represent sets using Venn diagram. We had also explained the Venn diagram as well, and different shape the kinds of set, and we have discussed subset, proper subset, equal set, and the power set. So for our week's references, I will just post the links for this presentation, most especially the videos that I have included in the presentation. So these are some of my references, and also we have some suggested readings, your handouts or printed modules as well, PDF files. And for week 10, we have requirements. So for our requirements for week 10, we have activity 1. So for activity 1, answer activity 1, we have 1, 2, 3, 4 instructions for this one. So draw A and C on a Venn diagram and place the numbers in the correct regions. Draw B and C on a Venn diagram and place the numbers in the correct regions. Shade A on a Venn diagram and place the numbers in the correct regions. And shade A on the Venn diagram and place the numbers in the correct region. So these are the instructions for your week 10 activity. So before ending this video discussion, I would like to say thank you and share Bible verse from the work of Mark chapter 9 verse 23. Said Jesus, everything is possible for one who believes. So thank you once again and God bless.